Alright, calculus, we are here looking at section 39, which is all about e to the x, or e to something. That number there for the exponential function. So, let's do it. So we're doing both derivatives and integrals here with e. Let's take a look at derivatives first. So here's e to the x, this middle row. Here's some x inputs. And if I were to plug in e to the negative 4, that's what I would get here. And then 0.05, 0.135, etc., all the way across. The weird thing is that when you take the derivative, you get the same thing. So what's this mean? Well, okay, well, let's kind of, it looks like the derivative of e to the x is equal to e to the x. That's what I'm thinking. Just to confirm it, let's do the derivative of e to the x using logarithmic differentiation. That means using logs and such. So if I were to start with y equals e to the x and then take natural log of both sides, I would get natural log of y equals, well, x. Then let's take the derivative of all this on each side, d dx of everything. The derivative of x with respect to x is just 1. And here, well, it's kind of simple. It's 1 over y times dy dx. We got some implicit differentiation here. So to get rid of the y and move it over to the other side, so I just have dy dx by itself, I'll multiply both sides by y. That tells me dy dx equals y. Check. That's interesting, because y was e to the x. So it's true. It kind of just wraps around itself, and every time you take the derivative, you're going to come back to yourself. So the derivative of the derivative of the derivative of the derivative is still e to the x, as long as you start with e to the x. Cool. Well, let's see how this plays out. Now, of course, we're not going to ask you if y equals e to the x, what's y prime? It's kind of obvious. It's e to the x. But what about chain rule? You know, where you got, let's say, some function u inside that exponential thing. Then you're going to wind up multiplying by the derivative of that chain here. So what I see in this first one, I see that u equals 5x. In other words, this top piece here is 5x. Then the derivative of that, du dx, is 5. That, to me, says that that's my chain. So it's like a chain rule. We got y prime equals, well, e to the 5x stays the same, because the derivative of e to the x is e to the x. So this derivative of e to the u is e to the u times the derivative of this piece, which is 5. That was super easy. Like super, super easy. So let's increase the difficulty a little bit here. So now I have not only a u, some function up top there, but I also have this constant that I have to watch out for. Well, that constant 4, we have y prime. The constant 4, it's just a constant. The constant multiple rule just stays there. It's like a tag along. So boom, that's done. Then I'm going to have the chain rule. It's like e to the 1 minus 2x, because the derivative with the e there is just itself. But then we got the chain, that leftover piece. What's the derivative of 1 minus 2x? Well, in this case, it's negative 2. Now, a lot of people would ask at this point, is that it? Is that the answer? Yeah, it is. And unless it's some type of multiple choice, you would have to simplify, where you do have this 2, which is negative, and this 4, which is positive. Together, they make negative 8 times e to the 1 minus 2x. Awesome possum. Keep going here. This next one is almost easier than the last one. It's got more common derivatives, I guess you could say. Well, this top piece here, x squared minus 3x minus 1, that's going to be our chain. That's going to be the piece that's here at the end. Or not the piece, the derivative of that is going to go here at the end. So what is the derivative of that? It's just 2x minus 3. And then this stays the same. E to the x squared minus 3x minus 1. times that. This is so easy. Well, let's do it again. So now I got some brown here. We got a constant. Ooh, now we got something. Square root of x. Well, that's the same thing as saying 2 times e to the x to the 1/2. All right, let's do some sub work here. We're going to sub out some of these jobs. So the first job that we really got to take care of is figuring out if u equals x to the 1/2, then what's du dx? That's not too hard, but it's not necessarily super easy to do in your head. Let's write it out. 1/2 x to the negative 1/2. Okay, that wasn't too bad. So the derivative is really going to be e to the u times du dx. Let's put these pieces in and see what it gets to be. So it's going to become, that's the derivative, by the way, that's what we're doing. Y prime equals e to the u, so e to the square root of x. Now here's something kind of interesting. I don't know if you saw this. That 2, the constant up front, I totally forgot about that. That stays there. It's that tag along again. Times du dx, which in this case is 1/2 x to the negative 1/2. Okay, of course things can be simplified. For example, the 1/2 and the 2, those simplify to just 1. It would be e to the square root of x. Now this x to the negative 1/2, that really means square root of x and in the denominator. So we'd have over square root of x. And there's our derivative. Y prime equals e to the square root of x over square root of x. Not too bad. Not too bad at all. Let's keep going. Let's go for orange. All right. We got lots of rules here. The name of this page is the combo page. Combo play. Combo. All right. We need to see what actions are going to happen. We got multiple rules interacting with each other here. So first thing I see is a couple of layers. I got an inside layer and outside layer. So I know that I'm going to have some type of chain rule. I also see that there's an e in here, so I got to deal with the whole e to something rule. So let's piece it out here. The derivative. Well, we start with the outside of the chain. The outside layer is that power, so it'll be a 2 and then a 1. The inside stays the same the first time. And then the outside, well, that's the derivative of this. And the derivative of e to the x is just e to the x. The derivative of 3, however, is 0. So this is just e to the x because the 3 went to 0. All right. Next, let's go red. We got y equals, ooh, I got two things multiplied here, like an a and a b. And then that tells me that I have product rule. Okay, so if I'm going to be doing product rule as well as e in here, let's deal with those. So a prime, if a is x, a prime's derivative of x is just 1. B prime, well that's kind of convenient too. B is e to the x, and b prime is also e to the x. So y prime, the derivative of y, or dy dx, is really a times b prime plus b times a prime. Now you put it all together, and we have a is x times b prime is e to the x. B is e to the x times a prime is just 1. So there you go. Is it simplified all the way? Maybe. You could factor out an e to the x if you wanted to, if you really, really wanted to. And you might see this like on an AP calculus test, but you might not. Alright, let's give ourselves some defined boundaries here. I'm going to go up to this point and not beyond. Alright, what do I see? First I see chain because I got layers. I got an outside part of the function and an inside. Next I see an e in there as well for that inside piece. So that means for chain rule, I'm going to start with the outside. Well, the derivative of the outside, derivative of sine, is cosine. I leave the inside alone the first time, but then I'm going to multiply by whatever that is, the derivative of that, pardon me. is e to the x, because e to the x and its derivative, same thing. So there you go. Proper notation, they would probably put this other e to the x in the front, so you'd probably see it like this, e to the x cosine of e to the x. But honestly, doesn't matter. Same thing. Number 8, what color shall we do? How about not white? How about green? There we go. Yeah. So I see with my little eyes here, I got a chain rule and an E rule. And it's the chain is actually the E kind of chain. It's like e to the u thing, which is going to give me e to the u du dx, which really isn't that hard in this case. Because if u is sine of x, then the derivative here is going to be cosine of x. So that tells me this is going to be e to the u, e to the sine x, times the derivative of that exponent, which is cosine x. Done dizzle. There we go. Let's keep doing this. Alright, now we're just going to make it harder because that's what we do. Let's make a vertical line in here. Give ourselves some clean workspace. There we go. Alright, so let's start with purple. So I got natural log of x plus e to the x. What's going on here? First we got a natural log. That's, you know, got layers to it. And it's natural log of u, which is going to turn into u prime over u. Well, let's figure out those two pieces. If u equals the inside here, then x plus e to the x, then u prime, the derivative of that is just 1 plus, well, the derivative of e to the x is again e to the x. So y prime is really u prime over u, which if I substitute those pieces in, it's 1 plus e to the x over x plus e to the x. Not too bad, not too bad. Let's keep moving here. The next one, quotient. So we got quotient rule. Quotient, that's long. And then we also have this e to the u thing to deal with. So let's talk about these pieces. You know, we're going to have y prime equals low d high minus high d low all over low low. And let's figure out what d high and d low. So the derivative of the high one, that's going to be, well, e to the 4x, but then we got to multiply by that derivative of the exponent, which is 4. And d low, that's pretty easy because low is x, so d low is just 1. Right, so let's put these pieces together here. Y prime, substituting things in, low is x, and the derivative of the high is e to the 4x times 4 minus high d low. Well, the high is e to the 4x, and then we got, what's the derivative of x? Just 1. Okay, so that's that. And low low would be x times x, or x squared. So I'm going to simplify this just because it looks like one that would be. I see that they both have e to the x, or not e to the x, e to the 4x. So I'm going to pull that out. Then left over, in the first term left over, I'd have a 4 and an x. And in the second term, there's always that 1. All over x squared. There we go. All right, let's do this next one. Very similar. In fact, there's some shortcuts if you really recognize the similarity in the structure. I'm just going to kind of go off the same ideas. We're doing quotient rule, but this time d high is 1, and d low is e to the 4x times 4. Right, let's see how this plays out. Y prime, of course, is this same pattern, low d high minus high d low, except now the low and the highs have switched. So low d high is going to be e to the 4x times 1 minus, Okay, high D low. That's x times e to the 4x times 4. All over, now we got e to the 4x squared. I can simplify that denominator there, but I actually want to leave it alone for a second. Because remember how we factored out that e to the 4x? That's going to affect some of the simplifying here. So I have e to the 4x times 1 from the first term. But the second one has the minus 4x. No big deal there. That's pretty straightforward. But now here's something that people might not think of. I can simplify this piece here and one of these on the bottom. So I'm going to take away that squared and this there. So let's mark those in the same color so you guys know where that came from. That black and that black there. Okay, so those go away, and not really go away. It's really just 1. Because e to the 4x over e to the 4x is 1. So now I have 1 minus 4x over e to the 4x. That totally looks like something they would do on the AP test. Why? Because it looks simple, but there are so many layers in that. All right, let's use a new color here. Blue looks good to me. I see chain, and I got some type of e in here. So first, I want to rewrite this. Y equals e to the x to the 1/3. Now this is kind of interesting because I don't really have to do the traditional chain rule here. I could do some algebra simplifying with these two powers. Whenever you have power to a power with these exponential steps here, you can multiply those. So this would be e to the 1/3 x, or x over 3, however you want to say that. Why is that useful? Because now when I take the derivative, this is really e to the u kind of thing. Then y prime is going to be e to the u du dx. All right, now going from there, u is 1/3 x, so du dx is going to be just 1/3. So y prime is going to be e to the 1/3 x, that stays the same, times 1/3. Written more simply, it'd be e to the 1/3, let's say x over 3, all over 3. Boom! Okay, we are about, a third of the way here. You need to take a break, do that, pause it, go back, review. Now we're going to get into the applied stuff. Applied, as in using these rules for various prompts. The first prompt here is saying implicit differentiation. Now, even if you didn't see those words, you should recognize that the derivative requires that because we got mixed x and y's here. I have mixed x's and y's. And notice here, I got a y, I got an x and a y, stuff all over the place. So what I need to do is just take the derivative. And I look at this and I see, these second and third terms here, this one here and here, these two, those won't be too hard. That's kind of like semester 1 work. But this first term, we got a little bit of extra things going on there because I have not only a product rule where I have an a and a b, but I have to deal with this e to a y, and that's kind of different. So let's take care of the second and third terms first, then work our way back to that first one. Easiest one, the derivative of 8x, that's just going to become 8. Derivative of 3y, minus 3y I should say, is negative 3, but because we took the derivative of a y, we got to put the dy dx on here. That's a little bit of chain rule happening. Equals 0, because the derivative of 0 is 0. Alright, so the structure here, I need to look at this as ab prime plus ba prime. Derivative of one times the other plus the switching of that. Okay, so ab prime, that's going to be x times e to the y dy dx. So what's going on there? How did I get that? Well, e to the whatever, take the derivative, it's still e to the whatever, but you have a chain, and which is the derivative of that exponent. And the derivative, this is interesting, d dx of y is dy dx. Why? Well, look at this. dy dx. Easy. Okay, so that's how that came there. Plus, whoops, we got more here, ba prime. Well, b was e to the y. And a prime, the derivative of x, is just 1. So that's, I could just leave that. Now here's one of the common errors. Don't do this, but a lot of people like to say, oh, there's a y that needed a dy dx. No, it didn't. It did not. The only reason you're thinking that is you see the y, but you only put in that dy dx if there's a chain rule because you took the derivative of y. We didn't take the derivative of y. We took the derivative of x. All right. Now that we're here, I gotta move stuff. So I'm gonna take this one and this one. I'm gonna move them over. A little bit of algebra going on. So that means e to the y plus 8. These dotted lines here, those stay. So we got e to the y plus 8 equals, and then on the other side I have x e to the y dy dx. But that's minus, actually. So I'm going to write that one second, just for cleanliness. So I'm going to have 3 dy dx minus x e to the y dy dx. And then from this point, I could factor out that dy dx. I'd have 3 minus x e to the y. And all this equals e to the y plus 8. So I'm going to divide both sides by this. 3 minus x e to the y. 3 minus x e to the y. Hey, look at that. I'm done. dy dx, got it by itself, equals this. That was cool. Let's try some more. All right, for this one, oh, this is an interesting function. I can't remember which it is, but it's either something called sinh or cosh. It's one of those. I can never remember which one's which. So let's just take a look at what's going to happen here. Kind of some interesting stuff. So the first thing is it says take second derivative. In order to take second derivative, I've got to get from first derivative and then move further on to second derivative. So let's start with first derivative. Well, that's pretty easy. These are straightforward terms here. E to the x, the derivative is just e to the x. We got minus here. Now for the second term, it's still e to the negative x, but I got to multiply by the chain the derivative of this negative, which makes this times a negative 1, which if I were to take that further, it's really e to the x, and then we got negative negative, so that makes a positive e to the negative x. That's just a little bit of extra algebra there. So why didn't that happen with the first term? The first term is just e to the 1x, and the derivative of 1x is just 1. And 1 times that is the same. So the derivative of e to the x is just e to the x. We knew that from earlier. But the derivative of e to the negative x is negative e to the negative x, or e to the negative x times negative 1. So let's look at second derivative. So the e to the x, that stays the same. But now the second one, that negative is going to pop down again. So we're going to have minus e to the negative x. Oh, this is interesting. Look at that. It's a cycle. So, oops, not there. All the way up to the top. You start with y. Y, take the derivative, you get to y prime. Take the derivative, you get to y double prime. But y double prime is the same as y. So you take the derivative, and it's this cycle. You keep going around. Because if I were to go to y triple prime, that's the same as y to the first. So you got this cycle. You just go back and forth from plus minus, plus minus, plus minus, plus minus. Kind of cool. So let's use that coolness. Let's look at the relative extrema for this function. Well, we've already figured out that y prime equals e to the x plus e to the negative x. and that y double prime, let's do a different color for this. How about red? Y double prime equals e to the x minus e to the negative x. So when I see the words relative extrema, here's some stuff that starts popping in my head. I start thinking y double prime equals, or y prime equals 0. But for the inflection points, I'm thinking maybe y double prime equals 0. And we're really looking for a change in sign. It's got to go from positive to negative or negative to positive for either one of these things to happen, relative extrema or inflection points. Those are all about change in the numerical values of rates or rates of rates. So in order to do that, sorry about that, got a little interrupted there by the custodians, but so what do we got going on here? We got first derivative, second derivative, extrema, inflection points. Let's do it. So for first derivative, I want to set these things equal to 0 because for something to change from negative to positive or positive to negative, they have to pass through 0. That's how it goes through that. So that would mean 0 equals e to the x plus e to the negative x. Well, this kind of presents a problem here because when I try to solve this, and let's say I move negative over negative e to the x equals e to the negative x. This is never really true because, well, how would you solve this? I mean, if I looked at this, I would say, well, why can't I take the natural log of this and the natural log of this? On the right side, that's not really a big deal because the natural log of e, those kind of undo each other, then you just have negative x. But on the other side, I have natural log of a negative. That's a problem. In fact, that's an impossibility, which means this just doesn't work, which means that's never going to happen. So there's no relative extrema. Okay, all right. Let's look at the second one then. Let's see if there's at least maybe an inflection point, which could happen. It's possible to change concavity, but never actually change decreasing or increasing. So let's see what we got. E to the x minus e to the negative x. Well, that is going to be equal to 0. Now, if I move this second term over, then I would have e to the negative x equals e to the x. Now I could take natural log of these because natural log of e, no negatives in there that messes me up there in the exponents, but that's fine. That's not a big deal. This just becomes negative x equals x. All right. Predicament. Because I don't know what you would do. Maybe you would add stuff to both one side. Here's what you can't do. If you divide by x on both sides, then you get negative 1 equals 1. That doesn't work. Scratch. Negative x equals x. Well, let's try adding x to both sides. That gives me 0 equals 2x. Well, x must equal 0. Check. It is true. In fact, there is an inflection point at x equals 0. That's cool. Now, if I were to check before and after, I would see, a change from negative to positive kind of thing, or positive to negative, and that would happen. I can confirm that, doing some work looking at x at negative 1, 0, 1, and e to the, or let's just say y double prime here. At 0, it's 0, so that's helpful. At 1, if I were to plug 1 to this, that's e minus 1 over e, which is a positive number. And here, this would be 1 over e minus e, which is a negative number. And I'm doing a lot of shortcuts, simplifying, abbreviating, and stuff like that there. But this is the values you would get. And you would start with a negative before, positive after. Changing sign, therefore changing concavity, therefore inflection point. All right, let's keep going here. Number 16. 16, 16, 16. There we are. Find the area of the largest rectangle. All right. That word is interesting. Largest. Well, when I hear largest, I think like the biggest, the largest, the most optimal size, which to me means this is an optimization. Optimization. So how do I do that? That means derivatives. That means maximums. So I got to take the size of the rectangle and I got to make it a maximum size. Okay, so let's see what we would start with. So we got 3 minus e to the x. Let's graph that. I'm going to go to my y equals here. And I got a whole bunch of things. Let's change this to a large screen so you guys can see. I'm going to clear that one off, clear the next one off. I want to graph in here 3 minus e to the x. And we're talking first quadrant, so I don't really care about any other quadrant. Let's start from 0 to 5. Okay, that's fine, 0 to 5. Okay, so I'm talking about a rectangle up in here. And in fact, it looks like, you know, I start at 2. It looks like I cross right around 1. So let's just change those values completely. Let's go from 0 to 1. And from like 0 to 2 or 3. Let's see what that does for me. Hey, look at that. So I want a rectangle in here. I want it to be big. I want it to be huge. How do I do that? Well, let's throw this in here. Let's look at this as a picture. So I just put this picture in here. And a couple of things that I want you to know. One, that this is 1 right there. This is 0. And this is 1, 2, and 3. So for me to find a rectangle here, that rectangle is going to be interesting because it's got a vertex or a corner is on this curve. And this point on the curve is an xy coordinate, meaning that this distance here is x, this distance here is y, and the area is x times y. Now, there is my function. The area of the largest rectangle. So the area equals x times y. That's my function that I want to take the derivative and you know, multiply. But wait a second. I don't even have to do implicit differentiation because I know what y is. It's up here. Y is 3 minus e to the x. So this is going to be x times 3 minus e to the x. That's helpful because now I can do I could even multiply this x here or however I want, and then I could take the derivative of that, optimize it, maximize it, make it big. Well, let's do that. So I see a product rule a and b, so I need to find a prime. That's just 1, and b prime is going to be 3 minus e to the x, which is really minus e to the x. Because it's negative 1 times e to the x, which is just negative 1 times e to the x. We took the derivative. Okay, so the area, the derivative of the area is ab prime plus ba prime. That's going to be x times negative e to the x plus 3 minus e to the x times 1. Okay, so we got x, negative x e to the x plus 3 minus e to the x. And we want to make this optimization. So I could do this probably with a calculator a lot better. Let's do that. So I'm going to go up here, and this is kind of interesting. Since that's my y, I'm just going to put in here x times, I'm going to go to my vars menu, y vars, and over to function y1. So I'm going to just say x times y1. That's all I really did here. They are multiplying, but if you wanted to be picky and put a multiplication symbol, there you go. X times y1. So that, hey, that second function here, this is my area. And I want to turn off the top one then. So I'm going to turn that off. Now let's look at it. It definitely looks like there is a maximum value about here. Can I calculate the maximum value? You betcha. You betcha. Maximum. Second calculate maximum. And sure, let's go from there. And we know it's between that point and a little bit further. That's good. Guess somewhere in the middle, about there. Boom! Answer. So the area is 0.707 and the x value is 0.617. So the area is equal to 0.707. But the x value solved from this equal to 0 would be, what was it, 6 something? 617? 617. 0.617. Boom! Alright. Let's keep more. Let's do more, let's do more, let's more. Let's keep on going. Ooh! Now we're into part 2. You know what? I'm actually going to split this video 2 parts. Mostly just because it's kind of like differentiation and integration. We just did derivatives. So I'm going to stop here. I'm going to make another one. And that one's going to be on the integral part. So there you go.